Let's begin. Welcome again to this course. And last time I left off with some survival tips. I just want to finish up with what's left on these slides. Not much going on, just to make sure I cover all of them. I talked a little bit about the survival tips. Homework is going to be important in this class. There's going to be a lot of coding activities because I want you to have tools for your future courses next semester and your research. Over and over again in faculty discussions, we want our grad students to know how to deal with data, how to analyze data, how to solve a system of equations, how to do this and that. This will not give you all the tools you need, but it will give you enough tools to cover 80% of the stuff that you need to do, and also set you up to know what you need to look for next. Okay? So this is what I left off, I think, last time. My goal with the homework is not to get the answer, is to actually think about how you're working through a problem. Okay, so don't focus on just getting an answer, focus on learning something, learning opportunity. Every homework assignment I will try to make it a learning opportunity for you to learn something new, to push you to the limits, so we will learn something in class. But again, this is grad school, so there's a lot of open-ended questions, and I will try to push the boundaries. You might need to do some research to learn something new I introduced to you in the homework assignment. Okay, so the answer is not to get the goal, is to think about things and practice those muscles and coding and thinking. Writing code is not the goal. So I don't care if you write code that is like the best code you see on Stack Overflow, which is like a famous website where people go and talk about coding, right? I encourage you to. I personally learned coding. I never took a single course in coding because I think those courses are generally not very helpful because they focus on the theory of coding, whereas I want to use coding as a skill, as a practical skill, because I'm an engineer, not a coder. I use code for an end. So I learned coding by copying others, and Stack Overflow was a big deal. I would, take their codes and adapt them to what I want to do, and by reading them, I learn something every time. And that's how I do it till this day, because I don't want to occupy my mind with the specific syntax, for example, like sorting an array and whatnot. But what I need to know is that I need to sort an array. Now, how do I sort an array in Python, in C++, in C, in MATLAB? That's mundane to me. That's not the important question. The important question to know is, okay, I need to sort the array now, or I need to take a dot product of two arrays. It's more important to recognize that than how to do it, because how to do it, you just Google it, or GPT will give you an answer for that, and then you pick up that syntax in your mind as you go along. Okay? Presenting your results is as important as the results themselves. So, that goes back to the homework. Your reports need to be readable and good. The thought about programming is that, my perspective is that the programming language is just that, it's a language. So how many of you do you speak any other language? Okay, how many other languages you speak? One more? No. One, okay. I speak 3 languages, okay? Now, but I can express the same idea in those 3 languages. So the language, if you think about it, is the clothing that goes around the idea. What's more important is the idea itself. Same thing with coding. What is more important is figuring out what you need to do. Now, you can say, I want to do this in Python, in C, in C++, in Fortran, etc., etc. But the idea is the same. So if you recognize what you need to do first, that's the harder step. Once you recognize that, figuring out the language, which is essentially the syntax of how you want to structure your solution, that's an easier problem to solve, right? So think of it 2 steps. What do I need to do? So that we call that pseudocode. Essentially like, okay, here in the first step, I want to create an array of numbers that I want to compute the derivative at. Then I want to evaluate the derivative by applying this formula. Okay, so to do this, I'm going to create an array. So these are concepts that are common across all languages. But how you do them differs per language. That's where you could do some research, you could Google it, you could ChatGPT it and whatnot. But the core concept is the idea. Okay? Now, there's a reason we chose Python, and in today's lecture, I want to explain why and justify to you why Python is such a big deal and why it's important. And I have some notes here for why Python. It's free forever. People were using MATLAB because they thought it is the best coding language for scientific application. It is not. I mean, it's a good language at the time. It served its purpose. But now, it's going to be, in history. And I'll show you some statistics that demonstrate that. Python will have the same fate eventually. Maybe in the next decade, Python is going to be a thing of the past. We're going to be using Ruby or some other even more modern programming language. And that's okay. So don't have an attachment like, no, I'm a Fortran coder. No, you know what? Yeah, tough luck. It is very easy to get started with programming with Python. It's very forgiving. So in the programming language world, we say that Python is not strongly typed. Type, not typing. Type is the data type. Like, are you working with integers, floats, strings, etc.? Python is not strongly typed. You can sometimes mix numbers, integers, floats, and strings together in one object, etc. With C++, for example, you have to strongly declare what type of data you're working with. Fortran, for example, is like that. JavaScript, more or less. The modern versions of C++ are not like that. They allow you some flexibility. But there's a price to pay for having this ease of working in Python. It makes it not the fastest programming language, but that's what's so great about it, because it allows you to do something really quick, really fast, prototype, have decent running code that is easy to develop and create, rather than having to spend months to write a fancy software with C++ or more advanced languages. Python is in high demand. These rankings keep changing. Right now it's number 1 and 2. And it's very forgiving. So there's a huge community of support around it. Anywhere you look up the internet, even XKCD, I think, starting to have like Python. You know what XKCD is? Yeah, so look up XKCD. Is this physics guy who he finished his PhD and then left it and started doing comics about physics stuff. And he's got like some really funny, it's very relevant to your PhD because he makes a lot of jokes about being a PhD student. It's called XKCD. So look it up. He's got like a comic every day. He has a lot of funny Python. One of them is like, I should have put it here. And actually, let me see if I can find it on the internet. Okay. XKCD, Python. Okay. All right, so I'm gonna move here. Yeah, so he's got a ton of, so it starts like, you're flying, how? Oh, Python. Like, I learned it last night. Everything is so simple. Hello world is just print hello world. I don't know, dynamic typing, white space. Come on, join us. Programming is fun again, etc. But how are you flying? I just typed import anti-gravity. And that's how it's going to be. We're going to import NumPy. We're going to import SciPy and other things. All of these tools are readily available for you. Okay? I should actually put this in the slides. Okay. So Python, good thing. Anyway, if you don't like it, you have to use it here. So unfortunately. And I explained this in the syllabus. All of you, I think, have Python set up by now, I hope. So I don't need to go through this. Now, it's your responsibility to learn Python, but I will also teach it to you. But I'm not making that promise, okay, because I don't want to be held accountable for that promise. So it's your responsibility to learn Python, but I will teach it to you in class as we go along. In fact, today's lecture, and if we finish, if I can stop going on tangents and blabbing about things, we're going to start coding, okay? And we're going to start doing some simple codes, but you will learn a lot with just this little intro. Now, if you already know Python a little bit ahead of the curve, that's okay. You might feel a little bored. that's okay. Maybe you can work on something else in the meantime, but we're going to get everyone up to speed, okay? Because there's going to be a discussion where one of your colleagues knows the topic, but you don't. So let's just be patient a little bit. But I apologize if you're going to feel a little bored with some of the things we're doing. And we got a lot of resources. Learning Python, your first assignment will have you cover this easy tutorial about Python that I put together. It's just like a bunch of slides, and I'll have you implement it yourself, okay? All right, so let's go. I had this action items for you to check, which I think you've already done. Review the syllabus in full. Nobody does that. One time I put $50 in a cubby in the department, and in the syllabus I said, like in the middle of one of the sentences, out of the blue, by the way, there's $50 located in Mrs. Bushman's, Christina, box. Nobody got that $50. Nobody reads the syllabus. But I always ask you to read it, okay? There's no $50 this time. I want to buy a guitar, so I'm saving. I'm not gonna give you $50, but anyway, so but try to read the syllabus, at least the relevant pieces of it. Install Python, subscribe to my channel, and so that you get alerts, because I post the videos there first, and then put the link back on Canvas. Allow me 24 hours, please. Usually I do it by end of day, but sometimes processing takes time, or I have to run and then do it at night. So give me 24 hours for the lecture to be up. Have your friends, family, and neighbors subscribe. Make sure you can log into Canvas. Make sure you receive Canvas announcements and Canvas emails. So I send announcements. Make sure you get an alert when there's an announcement about something. Find out where the help sessions are. We're still waiting for the poll to finish by Friday. So we will announce this, and familiarize yourself. Most of you are familiar with the space, but make sure like where my office is. We'll eventually add the help sessions, add them to your calendar. Find out where my office is, just kind of walk by. If my door is open, just come on in. And for Python, start with this link. It will be also on your first assignment. Okay, so I have a next set of slides to explain to you. Do we have a microphone here? We have speakers, but no microphone. Okay, we're going to have to listen very, very hard. Who watches movies? I like movies. This is a beautiful movie about our first mission to the moon, Hidden Figures. If you haven't seen, really love that film. Okay, so you might not remember this bit, but this. Oh, there's no sound. Why? Okay. Sound. Let me check something. Who was talking about Murphy's Law earlier? All right, output. Okay, well, let's try now.
What's it going to take to make this thing worth the price tag?
Well, we're just getting up to speed here, Mr. Harrison. I need more manpower. I need programmers, folks to feed the car.
We'll get them for crying out loud. All right? You're the IBM man, right?
Yes, sir.
We'll pull my old guy if you have to.
Understood.
I'm not paying any of you.
When the first IBM came to NASA, it was not an easy transition.
No one thought to measure these things?
I'm afraid not, sir.
Nobody knew how to use it.
Computers were these big units that took up the whole entire wall.
There's more computing power in a toaster today than what was available to these people in the 1960s.
When Dorothy sees the IBM being built, she learns how to program them.
She realized really quickly that the IBM was going to be the wave of the future.
The IBM 7090 data processing system. It has the ability to solve problems that cannot be solved in a lifetime of manual labor.
Hit it, girl.
What's your name again?
Dorothy Vaughn.
We need the IBM for Glenn's launch.
We got a job to do. Whatever happens up there, it's in God's hands.
My gals are ready. They can do the work. Ladies, we've been reassigned.
she basically saved her whole team's jobs and created a value for herself.
It's so funny what we think of as computers now and what they were then.
Okay, so, she had to program this crazy data processing system which did like a fraction of what our phones can do this day, right? But she was using punch cards and series of punch cards, and literally the people on her team were called computers before the computer came, because they used to compute things. They would give them these trajectories that they need to compute, and they would split the assignment like in parallel computing, and they were called computers themselves. And then comes this computer, and they learn how to program it. So the point I want to make to you, so I put this in my numerical methods course, is to encourage you and tell you, look, you can't live without computers. You have to learn how to talk to them. You have to code them. Coding is not going to go out of business. Even if ChatGPT is writing insane code, there's people who are still needed to interpret that code and fix it, because a lot of times it gives rubbish. All right. Also, if you like movies, have you seen Ratatouille? Right? Anyone can cook. So I really like that film too, because I love cooking as well. So we came up with this. Anyone can code with Python. Okay, so you can code with Python. Anyone can code. So, if you have some jitters about coding, don't fall in the trap of trying to philosophize about, oh, am I going to be a good coder? Who cares? Just code. Just start coding, and you will learn, and you will be fine. Okay. So Python. Why do we like Python? Because it is one of the, so I pulled this morning from IEEE Spectrum, and this is the link up there. You can look it up. So you can look at the Spectrum ranking, at the trending ranks in the market, and the jobs rankings. So you see Python, number 1, after it Java, JavaScript, C++, C, and then where's MATLAB? Oh, there you go. Hello, Sir MATLAB. I have nothing against MATLAB. I just hate coding in MATLAB. Anyway, but so yeah, let's pick it up now. This aggregates Python for all applications, not just scientific computing. Obviously, for us, we are more interested in science applications, correct? But in general, it can do web design, it can do servers, it can do controls, it can do computing, science stuff. So now, next, if you go on the jobs, this keeps, come on, okay. Next, if you look at the jobs, then you see SQL, which is a database programming language, and then Python right after it. So they go hand in hand. And sometimes combining Python with SQL is pretty good recipe for success. Then Java, JavaScript, and then again MATLAB at the bottom. Some of the other kind of interesting little languages there, like Mathematica, very useful tool that we use in my group for symbolic math manipulation. But that's what it does, only for symbolic math. The whole world is not doing symbolic math. It'd be really cool if, the presidents of the worlds were doing math competitions. This is another report from October 2021 to November 2022. Some guy compiled it about job demands in programming languages. So Python is right here. Interestingly, under JavaScript. JavaScript, there's more focus on web applications, so obviously there's higher demand there. But Python can do web applications and also computing. So hidden in there are also science applications. So 515,000 jobs, you're going to find a job. Okay? You'll be fine. So Python is important. Okay, why is this keeps animating? Okay. Now, what is this planet? Jupiter, right? This big red eye. It looks blue here, but it's the big giant red eye. Like the size of 100 Earth. Now, what is Jupyter Notebook? I keep talking about Jupyter Notebooks. Jupyter Notebook is simply a web application that allows you to create and share documents that contain code, live code that you can execute, not just syntax like you copy and paste it in Word. No, it's actual code that you can execute and run. You can put equations in it, you can put visualizations, plots, animations, and you can put explanatory text. And Jupyter Notebook has nothing to do with Python. So Jupyter Notebook was developed with a team with Python with the hope that they use Python in it, but it can support over 40 languages. You can do C or Fortran or R in Jupyter Notebooks. Okay? You have to set that up for it to work. Now, by default, Jupyter Notebooks come in ready with Python. So that's what you installed with Anaconda probably. So in general, you must install and use it locally. Now, what we've done, we've combined Jupyter Notebooks and Python to make a, so when you combine them together, the result is amazing. And we can make this easier with something called Jupyter Hub. So we've taken, or the people at Jupyter and Python, they've taken the concept of Jupyter and they said, okay, what if we put Jupyter on Jupyter Hub, we call Jupyter Hub, we put it on a server so that you don't even have to install Python locally. You can just connect to it with a web browser. That's what on-demand CHPC does for you. You just connect through a web browser, you save your file there, and you don't have to install anything on your computer. So we did this with our CHPC people, the Center for High Performance Computing. And the motivation is that I want to remove all the barriers of entry for students to adopt programming. So engineers have been famous, notoriously famous, for not liking to code. And so if we take down the barriers, my thought is we can encourage the barriers of entry to install it and get a license and figure out how to start it. Just go on a web page and you have Python. You can just code. So we remove the barriers to encourage you to code. And if you choose to use this method, so that will be the on-demand at chpc.edu, or you can use Google Colab. There are some other services out there. Or if you're advanced enough, you have your own local Python installation, maybe with Anaconda, and that works as well. Now, don't confuse Python, which is the programming language. That's the language, like French, English, Spanish, right? That's the programming language. Jupyter Notebook or Jupyter Hub or Jupyter, which is just a web application that allows you to mix code, text, and figures together. Anaconda, which is just simply a distribution of Python and Jupyter. There are other distributions of Python and Jupyter. You install them and you will have Python and Jupyter. It's just a different vendor. Think of it as a vendor. Anaconda is a vendor of Python. There are other vendors out there. And you'll often see or hear or have worked with Spyder or PyCharm or Visual Studio Code. These are simply code editors, like text editors that allow you to write code in a nice and fancy editor and that can execute Python or C++ or something else. We are using notebooks instead of Spyder and PyCharm. Reserve this for bigger projects, but for the projects we're doing in this class and for most prototyping projects, just use Jupyter Notebooks, connect them with Python, okay? And this is one option for how you're gonna be using, I know about 4 or 5 of you have already signed up for this. That's great. Others, I assume you have it installed because we're going to use it today. Okay. And on your first assignment, so I have a repository on the web called ChemPy. It contains a few Python-related tutorials. One of them I will assign to you in your first assignment. That's your introduction to using Python. But we will use, I think, after this class, you're not going to even need to do that introduction. Okay? All right. So let's be done with these two, and we hit the ground. There's one preliminary I want to do before we start actually learning other things. And this first lecture, I call it just packing for the road. I don't know why I called it that, but I want to use this to introduce some concepts, specifically the concept of error, that everything has an error in life, and as engineers, you are going to report numbers in the end, and you have to assess them and quantify them and qualify them with an error value. Say, my result is this much with an error of 5% with respect to this or that. Now, we're not going to go into statistical error analysis. That's it. Take my course in statistics, but we're at least going to look in a simple error in its simplest form. But I will also use this opportunity of error discussion to introduce you to Python. Okay, so some of the examples might seem silly, but the coding of it is not going to be silly. It's going to teach you a good lesson. Okay, so it's going to be an easy problem to solve conceptually, but the coding is going to be a little harder, so we can focus on learning the code. Okay? I'll start with another example. I love rockets. So my PhD was in solid and liquid and hybrid rocket motors. So I love anything related to space and rocketry and stuff. Yeah.
It's the 4th of June, 1996, and the European Space Agency is launching its brand new Ariane 5 rocket for the first time. This is a big deal. The Ariane 5 is designed to carry large, expensive scientific and commercial payloads into space and heralds a brand new era for the ESA. A decade of design and testing and billions of euros have led up to this day. The Ariane 5 rocket carries no astronauts. The first payload is 4 very expensive scientific satellites to be delivered into orbit. Things start well. The rocket clears the tower and accelerates smoothly. And then the rocket abruptly changes direction, starts to break apart, and suddenly explodes. Less than a minute after launch, huge chunks and glowing fragments of Ariane Flight 501 rain down over the launch area. A shocking disaster for Ariane and the ESA. The cause? A simple, utterly avoidable coding bug. Okay, here's what happened. The Ariane 5 leaves the launch pad and accelerates smoothly into the sky, following its predetermined path towards space. Inside, the onboard guidance system is constantly tracking the rocket's trajectory and sending the data over to the main flight computer. To do so, the guidance system converts the velocity readings from 64-bit floating point to 16-bit integer. Okay, stop for a second, and let's think about what that actually means. Computers store numbers in a variety of ways. Consider 4-bit integers. 4 bits can represent anything from 0 to 15. But if you want to represent the number 16, well, there just aren't enough bits, are there? 16 is too big. You need more bits to store bigger integers. With 16 bits, you can store anything from 0 to 65,535. Or, if you throw in a sign, then 16-bit signed integers cover everything from minus 32,768 to positive 32,767. But anything bigger than that, and again, you've run out of bits. Floating point numbers are stored a bit differently. They're stored as a decimal, or significand, and an exponent. The details aren't really important here. All you need to know is that 64-bit floating point can store much larger numbers than can fit into a 16-bit integer. So converting between them can be tricky when the integer runs out of bits. So what does happen when you run out of bits? Well, if you're using 16-bit signed integers, the conversion will just wrap around to the beginning again. But whatever the details, you're definitely getting the wrong answer. This is known as an integer overflow. Right, so back to our rocket. The guidance system reads the horizontal velocity data of the rocket as 64-bit floating point and tries to convert that into a 16-bit integer to send over to the main flight computer. But at that moment, the velocity reading is actually larger than the largest possible 16-bit integer. The system tries to do the conversion and fails. Now, a clever system would have some procedure built in that says, hang on, we're piloting a rocket here. I need to say something sensible to the main computer. It would have some overflow error handling code. But in this case, guidance system code isn't very clever. So it just sends an error message in place of the velocity data and promptly shuts down. Fortunately, there's a backup guidance system in case the primary module breaks down. Unfortunately, it's running the same code. So it does the same conversion, gets the same overflow, and crashes for the same reason. The main computer receives the error message, and because there's no handling code built in, the computer interprets the message as real navigational data and immediately freaks out. The velocity reading is off the charts, indicating that the rocket is dangerously, impossibly off course. So the flight computer does what it's designed to do. It fires up the boosters and drags the rocket around in an attempt to rescue itself from a non-existent disaster. This puts the fuselage under incredible aerodynamic strain, which starts tearing the rocket apart. Detecting that things are now really going badly, the computer calls it a day and triggers the built-in self-destruct mechanism. So, what was the ultimate cause of this incredibly expensive, very short, and ultimately catastrophic rocket flight? A simple line of code, converting a floating point to an integer that led to an overflow passed without warning to the main computer, which was interpreted as real, if wildly inaccurate, data.
The look
The
and
flight software had been used previously with no problems on many flights of the smaller Ariane 4 rockets, but the Ariane 5 was designed to fly faster than anyone planned for when the software was originally written, and the higher velocity led to the overflow error, a flaw that should have been found. It just never came up. Want to know the worst bit? That buggy bit of code wasn't even necessary during flight. It was part of the launch pad alignment process and shouldn't have been running after liftoff. But sometimes a small glitch somewhere causes a launch to be delayed by a few seconds. So to save having to reset the system, the original programmers decided to keep that bit of code running for 40 seconds after the scheduled liftoff time.
It only lasted one more second. Anyway, so errors are a big deal. Okay, now this type of error you are not going to be dealing with, but errors are a problem. Okay, and coding errors can cause problems, etc. Thankfully, with modern computers, we rarely see this kind of stuff, but this programming error is a type of error we face. Now, you will see in my slides the following colored things. When you see a box in blue, this is a general activity that I might tell you to do in class. When you see this in like this greenish blue box, this is a coding activity that we're going to do together. A definition is in a gray box. Code snippet is in that nice little framed box. An important statement is in yellow box, and an example that we do together in class is in this bright green. Okay, so the first activity is, what is, and I'm asking you, what is x minus 1? 1, right? Okay, exactly 1 for any x. Okay, so let's go ahead and do this in Python. Open up your Jupyter notebooks. Okay, so we're going to open up this Jupyter notebook, and we're going to put x minus 1. We're going to try it with a few values for x, and then we're going to do it for 1e to the 16, so 10 to the power 16. Right, so open your Jupyter notebook. If you haven't done so already, you can start it from your Anaconda or go on the CHPC. For me, it's already here. Okay, let me grab this to move it to Retina. Okay. So when you open your Jupyter notebook, you're going to see your file directory, your folders, and all right, so lectures. So like on my end here, let me show you. As I browse to the correct directory, I'm here on Google Drive, Chemical Engineering 6400 Foundations, Fall 2025 lectures. We are here in preliminaries, and I'm doing here errors and basic coding, and I have a bunch of activities here. Okay, so I'm going to create a new notebook. You just pick whichever Python you show here. There's Python Anaconda environment or Python whatever. Just pick any one of those, and that should create a new notebook for you. It showed it right here. Okay, so we're going to open that, and oops, let me close this guy. Can you see in the back? If you have the newer version of Anaconda, it's going to show you this little weird things on the side here, which is utterly useless, I think. Okay. Hold on. Let me try this again because I do not want to see that thing on the side. Okay. Okay. So this is what you will see, right? This is what you will see. There are, like I said last time, there are code cells and there are text cells that you will see in a Jupyter notebook. Many of you already know this, so bear with me for a few minutes for those who are just kind of getting to know Python. So if you go here, and you can change the cell from code to Markdown. Now remember, I said that Markdown is the language that we use to write text in Python. So what I want to do here is say coding activity 1. And if I press Shift Enter, it's going to turn it into text. Now, I want to make this a heading, like a title maybe. I'm going to put a sharp symbol and a space and press Enter. Look at that. It made it a large heading. Okay. Now, again, on this one, I'm going to also convert this into a markdown cell. And I will write in this notebook. So I'm trying to guide you into what I would expect for a discussion. I am not going to do this all the time because I don't have time in class to write discussions. It would take us forever. So in class, you will have to excuse me that I will hit the code directly. But in your homework assignments, I expect you to write code. Don't say Professor Saad in class just does coding without discussion. I expect you in your homework assignments and reports to write discussions. Okay? So I'll write a discussion here just with you for a little bit. And then we will just do coding. In this notebook, we will evaluate numerically what x minus x minus 1 is for a few values of x. Okay, so when you execute this, it's going to give you this x minus 1, but this is ugly. This x is not math. This x looks like just any other text. So I need to make it math. So I'm going to put a $sign around it here, a $sign. Now it looks into beautiful math. That's it. That's LaTeX. So we're blending LaTeX into the Markdown. Okay? If you haven't done so already, look at the cheat sheets for LaTeX and Markdown in the files directory in the supplementary material on Canvas. Okay? So everywhere you have a variable or math, I want you to write it in LaTeX. You will lose credit for not using LaTeX, okay? Or not using appropriate math. It looks very nice. All right, so let's begin some coding. With Python, you just start coding. So first, I'm going to put a value for x. So let's say x equal 0.5. Okay, and then I want to evaluate x minus 1. Now, if you do this and press Shift Enter, it's just going to give you a value. That's how easy Python is. But right now, we're using it as a calculator. What I've done here, I assigned a value for the variable x, and then I evaluated on a new line x minus 1. So 0.5 minus 0.5 minus 1, it's 1 as expected. Okay? We'll make it a little bit better. For better programming practices, I would never leave a statement like this without it being assigned into a variable. When I say assign a value to a variable, it means I'm going to store something in memory. So when I say x equals 0.5, what the computer is doing is taking the value 0.5 and putting it in a location in memory that we refer to as x. So everywhere later when we say x, it's going to say, what is x? X is in memory, and it contains the value. It's a bucket that contains 0.5. Okay? Same thing here. This is a value. X minus 1 is a number. It's better to store it in its own variable. So what I would call this is result equal x minus 1. Now when you do this, nothing is automatically printed because Python is just a variable assignment. You didn't do anything. So to see what's inside result, you have to print it. So you can simply print result, and it gives you 1. And many of you know this. For those who are new, this is pretty straightforward and easy. Now, this is not sufficient for a discussion, so pretend we don't see this in your homework assignment. You have to put a discussion here and say, my result of this operation is 1. Okay? But print it to see the result yourself, but you have to report it. Now, even better, you should qualify what you're doing. I would say put my result is equal result. So what I did here, I put text in my printout statement. And text is placed in quotation marks. I said my result is equal to, and then comma, and then put the numerical value. So Python then says, OK, I'm going to print these things. I'm going to print my result as instructed, my result equal, and then comma, what is next? What am I printing next? This result. What is in this result is the value we calculated. Okay? Good? Great. Okay, so now let's do 1,000. It's still 1. Let's do 10,000. Still 1. So we're going to need a lot of zeros. Let's do 1e to the 6. It's still 1. 1e to the 7. So that's 10 to the power 7. 10 to the power 8. 10 to the power 12. It's still 1. 10 to the power 16 is 0. It's 0. And any larger number is going to return 0. Because what happened in this case is that this number is so big for the computer to handle. And when we did the operation, when we did x minus 1, we couldn't do 10 to the power 16 minus 1. It couldn't fit it. It couldn't see the 1. So it returned 10 to the power 16. And then what it did, 10 to the power 16 minus 10 to the power 16. Okay? So be careful. The math, what you write here is not exact math. This is numerical math. Are you going to run into a problem like this? Probably not. But be careful what you expect, and always check as you're working through. So I give this example just to tell you, like, don't trust anything. Okay? Be very skeptical. Have a good dose of healthy skepticism as a scientist of everything you see. Even if an expert tells you, okay? There's no authorities in science, there's only experts, and even experts can be wrong, okay? So this is what you get in this case, and this is called round-off error. I talk about that in numerical methods course. In my numerical methods course, you need not to worry about this. In fact, I still have here some numerical methods from some inherited slides, so that's okay. Now, what are the sources of errors? There are modeling errors. So for example, you use an incorrect drag model for your application. You're throwing a parachute or deploying a payload at very large speeds, and you use a linear drag model, whereas you should be using a nonlinear drag model. You're estimating dropping a payload on Mars, for example, and you use something that is completely unrelated to the atmosphere on Mars, so you're going to get an error, a kind of error. That's a modeling error. It's not a human error, it's more of a misjudgment. There are programming errors. You put a mistake in the code, you do a wrong conversion, you treat a number as a float, whereas it should be treated as an integer, or vice versa. There are measurement errors when you go in the lab and make an error in your measurement. So for example, your sensors are not properly calibrated, or you're doing an air quality measurement and your intake fan is clogged. So you have some measurement error, or you put your radon sensor in the wrong spot. There's a human error in using the sensors, not setting them up correctly. So all of these are all kinds of errors. Numerical errors, which are our generally main concern here, but we might talk about modeling errors a little bit as well. But in general, for numerical errors, we have what's called round-off errors. That's the error that caused the Ariane 5 rocket to get demolished, and what caused this x minus 1 example to give you the wrong answer. These are called round-off errors. We're not going to talk about them much. There are truncation errors. We will come back to truncation error later in the semester when we had partial differential equations. And these are due to truncating a full mathematical formula. Like you have an infinite sum to compute a quantity, but then you can't compute an infinite sum realistically, so you truncate it. You say, I'm going to compute the first 200 terms, and the rest is called a truncation error. Okay. So next, we're going to look at calculating errors in practice. And again, this might seem just kind of naive and simple, and you know it. I agree 100%, but I'm using this as an avenue to get you up to speed, to get your hands wet with some coding skills, because we're going to need them in the next lecture. So I will define a couple of errors. These are the simplest types of errors that we define. When we say a numerical error, typically, even a first grader can understand this concept, is that you measure something and you compare it to some truth value. Okay? You're measuring a table, the table should be 1 meter long, but you measure 98 centimeters, okay? And so there's an error there, and that defines, when you have a true value or a truth value, then you call this the true error. It's simply the difference between a true value and an approximate value. Okay? True value minus approximate value, that defines an error. And often we report this in absolute values. You know, it's this obvious statement. You take a true value that you know is true, typically coming from an exact analytical formula, for example, and then you subtract your approximate value that's from your method, from your measurement, from your sensor, and you compare the two. Now, we're going to talk a lot about true value. There's actually no such thing as true value, but at least this sets the stage for our discussion as we make this a little more complicated. I'll go through a very quick example by hand, and then we will do this we will do something similar in Python subsequently. So, for example, here's a really simple example. Derivatives, sometimes some functions are complicated to compute derivatives analytically for. Okay, or in other situations, you don't know the function you're dealing with, you just have values of the function, and you want to be able to compute a derivative for that. So you approximate the derivative. This is a standard formula that you use in high school, the limit, or the rise over run, the limit of f of x plus some small number minus f of x over that small number. In the limit, as that's h goes to 0, that small number goes to 0, then you get the exact definition of the derivative, right? F prime of x is the limit of f of x plus delta minus f of x over delta. As delta approaches 0, then you get the true definition of the derivative. Numerically, we're like, okay, we cannot push delta to 0 because we're going to get 0 over 0, which is undetermined. So if you put a very small value for h over here, you can truly approximate the derivative, but with an error. So the example we're going to work with here, we have this formula to approximate the derivative. This is also called the forward Euler formula, which we will be using in the future. Again, we will redefine that later. H is some small value, okay, arbitrary small value. Now, for this is a general formula for a derivative. For the function, 2 times exponential of 0.5x, find the true error in evaluating f prime of 3. So we're going to evaluate the derivative at point x equal 3 using these two small numbers, 0.5 and 0.05. Okay? Now to do this, so we're being asked to find the true error. So I need a true value and an approximate value. The approximate value is going to be given by this formula, correct? We have x and we have h. We plug them in and get a value. The true value is we're going to compute that analytically. So first we will get the true value from the definition of the derivative. For f of x, 2e to the half x, the derivative is e to the half x. That's f prime of x. The true value is at x equal 3. So that gives us, we simply evaluate this at 3. So it gives us 4.48169, whatever, some number. Next step is we will calculate the approximation. Again, this is just a simple example. Okay, so now we have the true value. And then we do the approximation. This is the true value. Our approximation formula is this guy, f of x plus h minus f of x over h. And we want to do it for a couple of values of h. First, for h equals 0.5, you simply plug in x is 3, h is 0.5 minus f of 3 over 0.5. And you will get a value. Okay? You're going to get 5.09165. So that's your approximate value of the derivative at 3. And this is your true value of the derivative at 3. You take their difference, put them in absolute value, and you get 0.60997. I have no idea what that means, but it's a number. Okay? So we're going to build on this now. So what happens now when I shrink that h? What do you think is going to happen? That's what's important when you're thinking about your homework assignment. This answer, okay, good, I got the answer. Anybody can do this. What's more important is to think, what is going to happen when I go to the next value of h, which is 0.05? What is going to happen? What do you expect to happen? The error will be lower. So that's your hypothesis. Okay? So now you're probably starting to learn an intro to research about hypothesis-driven research. So anytime you're faced with a situation, come up with a hypothesis. The hypothesis here, your colleague said, my hypothesis is that as the value of h goes down, so does the error. Agreed? That's what our intuition should tell us. And that's frankly what the definition of the derivative is. Because the definition of the derivative is in the limit that h approaches 0, this should become exact derivative. So indeed, as h becomes smaller and smaller, we should expect the error to be smaller. That's what's more important in problem solving, because you go and run the calculation and you get a larger error, then you know that something is wrong. I must have made a mistake. Okay, that's critical thinking. Hypothesis-driven work, critical thinking. Okay, so let's see with a smaller h. Again, it's the same formula. Just you can do this with your calculator. You put the f prime. Indeed, you get some number that's, the other number was like 6.0 something. This one is 4.5, pretty close to 4.48. And then the error is 0.05. Okay, so the previous error was 0.6. This error is 0.05. So it's 1 order of magnitude smaller. Indeed, we did cut the error significantly by using a smaller value of h. So the number might be wrong, but at least you are consistent in, you might have made a mistake, a typo in the number, but at least you are consistent in that your error did shrink, and that should give you confidence that what you're doing makes sense. Okay, so that's true error. Put absolute values or not, doesn't matter. This error, however, does not tell us how bad the error is. So, okay, we got 0.6 and 0.05. Is this good or bad? Is it a big error or a small error? I don't know. I know the error went down, but still, did it go down? Is 0.05 a large number in the error or not? I can't tell. I have to be able to tell, I need to measure it relative to something else. So when my son comes and tells me, oh, this is big, and this is small, and this is small, and like, well, no, like this is big and this is small, but then I tell him, but this is big and this is small, right? So then he knows, this is bigger than the key, but smaller than the laptop. So that's what we need. We need something to measure the error relative to. I give you this example. A 1-foot error in measuring a 1,000-foot bridge is insignificant compared to a 1-foot error in measuring a 10-foot table. Because this error is 10% of the table. This error is 1/1000th of the bridge. It's insignificant. But it's the same value. It's still 1 foot and 1 foot. Same value of the absolute error. But relative to what you're measuring, this one is insignificant. It's a 1,000-foot bridge. 1 foot is not going to make a difference. But in measuring this table, and you commit like a 30, 40 centimeter error, that's a big deal. Okay? So then we define what's called relative true error or a relative error. And simply we take that difference of the true value minus the approximate value and divide it by the true value. So that's what we're measuring. This is the error, and we're going to measure it relative to the true thing, because we have the true thing. That's the 1,000-foot bridge. That's the 10-foot table. Okay? So error divided by that true value. So now this gives you a dimensionless quantity. It doesn't have any dimensions or units, and you can express it as a percentage. You can say the error is 10% or 5%. Okay, and then people will immediately know that you're measuring this relative to the true thing that you're reporting the error relative to the true thing you're measuring. So we typically report this as the error over the true value, so the relative error times 100%, so in absolute value. So that gives you a fraction or a percentage. Okay, so again, here, same example, a 1-meter error is committed in measuring a 100-meter bridge and a 10-meter bridge suspension. Which of those errors is worse? Again, you do the calculation. It's very simple. I'm giving you the error here. So in the former case, when doing the bridge, the error is 1%. And when doing the suspension, the error is 10%. So the error in measuring the suspension is significantly larger than the error in measuring the bridge. Okay? Now, okay, so this is true error. Anyway, this is error. The point is, error is the difference between two things measured relative to something else. Okay, now we're going to fine-tune this a little bit because I'm going to make an argument that a true error does not make sense. And you've probably heard me say this before. Because if we knew what the true value is, well, you don't need an approximate value. If I know the bridge is 1,000 feet, then it's 1,000 feet. Why do I need to worry about measuring it? Well, that's generally correct. But in reality, there's two issues. First, we don't know the true value. There are only like 2 cases where we know the true value of something. But second, you are also sometimes testing a new device, a new sensor, a new tape measure, right? And you know a bridge is 1,000 feet, or you know a mathematical formula gives you this correct answer, and you have a method to make, because the mathematical formula is expensive to evaluate, but you can evaluate it and get the true value. But then you have a method that's much cheaper computationally, but how far is it from the true value? Okay, so that's called verification, right? So oftentimes when you're designing a new experimental device, a new assay, a new blood test, you measure it compared to some truth, okay, to some other standard, right? So then in that case, you call that the true value, okay? And then you call that a true error. And that is valid when you are measuring compared to something you know in truth, okay? There's no absolute truth in the sense that we're going to discuss here. So this gets a little philosophical, and then we come back and be grounded in reality. So then, how do we get an idea of the error when we do not know the true value? Okay, so now you're like completely flying blind. How can you tell what the error is when you don't know the true value? Because if you know the true value, you don't need the approximation, or you don't need the other method. And I said already that, okay, the true value in limited cases where you have an exact analytical solution. So we will see later, when we are working with linear systems, you're going to implement a method or an algorithm on your code. What do? You test it on a small 2x2 system where you know the exact answer, and you make sure your code is giving you the correct answer. And if it gives you the correct answer, good. But then you take your code and run it on a 1,000 by 1,000 system. How do you know that you are getting the right answer or what the error is? We need a way to measure that. Okay? So I'll take you on a little detour here, and suppose, with some beautifully generated GPT graphics, okay, suppose that you want to compute the exponential of 0.3, e to the 0.3. You can grab your calculator, and that calculator gives you a number, right? You put e 0.3 and gives you a number. Okay? That's good. However, that answer that the calculator gave is actually not the true value. Although we treat it as the true value, but it is not the true value. Just think about it. How does the calculator compute e to the 0.3? What is e? Like, how do you compute an exponent? There's something going on in the background that is converting that exponential into something that is fundamentally just additions and multiplications, something much simpler, something that we can actually do by hand. So nobody can do e to the 0.3. There's like e to the 0.3. How do you do it? So the calculator is giving you an approximation to the true value using some type of approximation actually called the Taylor series. Okay? And here's my punchline. Outside of exact arithmetic, integer arithmetic, or rational numbers, like fractions, every value you measure and compute is an approximation. Integer arithmetic is the only exact thing you can do in computing. Everything else is an approximation. And rational numbers also, you can do them exactly, right? Okay. So your calculator is in fact expresses these functions in terms of simpler polynomials that can be computed with multiplications, additions, and subtractions. That's the only thing we can do: multiplication, addition, division, and subtractions. Okay? So in reality, e to the x, one way a calculator can compute e to the x is through what's called the Taylor series, and it converts this into 1 plus x squared over 2 plus x cubed over 6, and so on and so forth. Now these numbers we know how to calculate, right? Because they're products. We know how to do multiplication. We know how to do addition. The calculator knows how to do those elementary operations, okay? But then how does the calculator know when to stop? When to say we've reached the ultimate value of e to the 0.3? Okay, let's try it out. I don't know, but let's try it out. So let's say the calculator takes the first term to approximate e to the 0.3, and that first term is 1. Then takes the first two terms. It's 1 plus x, which is 0.3, so that's 1.3. And then it continues, okay, with 3 terms. We get 1.3, which is 1 plus x squared over 2, 1.345. Okay, now math theory, we trust the mathematicians, tell us the Taylor series converges. So it's not gonna grow indefinitely, it's gonna get to a finite number. Despite we're adding an infinite number of terms, it's just gonna get to a single number, okay? But that number is being refined, so we still need to add terms because 1, 1.3, 1.345 is changing quite a bit. And then 1.3495, and you keep adding terms. So what I did, I built a table here with 1 term, 2 terms, 3, 4, 5, 6, 7, 8, all the way to 20 terms. Okay, now here's my question to you. Is there a way you can tell the calculator when to stop? Okay, well, you already answered, so I'm gonna, okay. Okay, let's say whatever calculator is gonna look something, maybe the numbers it's gonna take 20 terms to get to this value or 10 terms, but internally, what can the calculator say? It's generating a table like this. What can the calculator say when to stop?
Look at the difference between the result and the past result.
Okay.
I was going to say that. And you can set a tolerance on those.
Okay. So can you explain more?
Yeah, so like, for example, looking at these, you can see there's a cutoff 12 and 13 where all of a sudden there's no more change.
Okay. So your colleague is saying, we look at the answer and compare it to the previous answer. Now, just visually looking, you're like, okay, it's changing, but it's only changing after like 7 or 10 digits. And then there's a point here from 11 to 12, and then from 12 to 13, it doesn't change anymore. And then from 13 to 14, it doesn't change anymore. Your calculator can't do any better. That's the best thing it can do. So then you could say, well, if there's no more change, I'm going to stop. Or if the change is less than 1%, that's called a tolerance, then stop. And you can implement this in any calculator, and the calculator is going to declare this as your true value, as the true value. Okay? So that's what happens in practice. So here's a column where I took the difference between the current approximation and the previous one. So with the first approximation with 1 term, we don't have a previous approximation, so we cannot compute a difference. But then after 2 terms, we can compute a difference between 1.3 and 1, so the difference is 0.3. But then between 3 terms and 2 terms, the difference in the answer is 0.045. And then you continue the difference between, so this difference here is the difference between this answer and that answer. And 0.0003 maybe is large or maybe is small. So you decide and say, when the difference is less than 3% or 10% or 1%, stop. Okay? Stop. And then, because the calculator and your computer actually in practice cannot do any better, because that's the best it can compute with, because it has a limited ability to calculate and store numbers. So this leads us to the idea of approximate error. What we did here is we don't know the true value of e to the 0.3. The calculator is actually trying to approximate it for us. Okay? Now we take the answer from the calculator and call it the true value, but actually the calculator internally is trying to figure out the best value it can give you. There's no true value. There's no true value ever. You are always dealing with approximations, and you're comparing one approximation to another approximation. Your calculator might give you a slightly different answer than my calculator or his calculator, because your calculator might have more computing power, but it's still not the true value, okay? So what we did here is called an approximate error. We said, we don't know the true value of e to the 0.3, but at the same time, we know that the Taylor series is converging. So we know with more terms, we're going to get to the true answer, but we can't compute an infinite number of terms. And besides, it's useless. We get the same answer over and over again, right? So we're going to say, okay, stop when the difference or the approximate error between 2 consecutive approximations is less than 10% or 1%, and declare that as acceptable error and report that value. So that leads us to the concept of approximate error. The approximate error in the context I presented is the difference between a current approximation and a previous approximation, okay, and a previous approximation, assuming that a current approximation is a better approximation than the previous one. In the Taylor series, it works because we know with more terms, we get a better approximation than with less terms, because the Taylor series is a converging series, right? And in most cases, this is the situation. You will see later when we are solving heat transfer in a plate, the more points we add on that plate to do our approximation, the better our approximation is going to be. We don't know the true value of the temperature distribution, but then we can compare a solution with more points to a solution with less points. Okay? Now, you can also frame this as the approximate error with the difference between a more accurate approximation and a less accurate approximation. Okay? So if you have a method, in practice, you might be developing a cheap sensor to measure something in the breath, okay, like tuberculosis, something like that, right? But then, how do you measure the error in your sensor? You go and take the existing high-quality sensor that was developed and verified and validated, and you call that as a better approximation to your sensor, because that other sensor is also an approximation to the truth. Again, we don't know the truth. Okay, we don't know the truth. Now, sometimes I guess in human studies, you might know that, like, if someone has the disease or not from symptoms, etc. But in general, you're comparing one system to another, and you have to weigh which one is more accurate than the other. Okay? Now, the most important piece here is that you can also declare a relative approximate error, which is also your approximate error, however you call it, current approximation minus previous over current, or more accurate over less accurate, minus less accurate over the more accurate approximation. Okay, that gives you a relative approximate error. You put it in absolute values and multiply by 100%, so that gives you a percentage error. So then you say, the approximate error in my system is 5%. Okay, so that tells me, when you come and say my numerical method or my calculation when I'm solving this partial differential equation or this system of ODEs for computing the kinetic rates, okay, my error is 5%, my relative approximate error is 5%, then I can trust that your method that you used, you compared it to a more accurate method, and the error was in that range, about 5%. Okay? So we'll do an example, and I think it's best if we do this. We can probably do this in Python. Okay. So again, I'm going to come back to the first derivative, not because I want to teach you about first derivatives. Again, the examples are mundane, but I want to teach you the concept of the error and the coding. It's going to get a little intense in a bit. Okay, so this formula, we take it again, and here I call it the forward Euler formula. So that's your definition, rise over run, how much you're rising for every h you are moving on the x-axis, how much is your function rising. So that's the definition of the derivative. Again, that's an approximation to the derivative. Now, we're claiming we don't know the true value of the derivative. So we're going to take the same example. We're going to evaluate it for f of x equal to e to the 0.5x. And we want to find the relative approximate error in evaluating f prime at 3 using h equals 0.5, 0.25, 0.125, and 0.0625. In the absence of a true value, you are looking for a better approximation compared to a worse approximation. So how do you assess this from here? Well, we know as h decreases, that's your intuition, that's what we demonstrated earlier. As h decreases, the approximation is going to get better because the true error was shrinking, as we shown before. And from just the theory, as h approaches 0, we're going to get better and better approximations. So what I'm going to do, I'm going to compare this approximation to that one, and the approximation using this h with the approximation using that h to compute a relative error. The approximation using this h with respect to this h, and then this one compared to this one. Okay, let me do it on the slides, and then we'll go in Python. Okay. So I'm approximating f prime of 3 using this formula for different values of h. For the first value of h, I have 0.5. My approximation is 5.09. I can't compare this to anything else because I don't have any other h values. Okay, so that's your starting point. There's no approximate error here. Next, when my h is 0.25, I have a better approximation because h is smaller. And now I can say better approximation minus worse approximation over better approximation, and that gives me an error of 6.66%. Okay? And that you can say, yes, using h equals 0.25, our error is around 6%. Our relative approximate error is around 6%. Now let's cut h in half. So h is 0.125 now. We have 4.62. I'm going to compare this to that. I can compare this to this one. It's valid. But since I have this value, reason and rationality tells me just compare it to the closest one. So this gives me 4.62. And this is better approximation minus worse approximation. So now 4.77 is a worse approximation compared to this guy. Whereas here, 4.77 was a better approximation compared to 5.09. See the relativeness? And then over the better approximation gives me an error of 3.22%. And then I cut this in half. Again, gives me a better approximation. And then compared to this worse one, better minus worse over better, it gives me an error of 1.59%. Okay, and you can say like our method, using the forward Euler method, you know, I'm getting these kinds of errors. Now, what is more important here, not the value of the error itself, but how the error is changing as h is changing. What can you see? What can you observe? Pardon me? Sorry, who said? Okay.
As you decrease age, your approximate error goes down.
Okay, and that's to be expected. But what's a more nuanced observation? Okay, the error is cut by half, but when h is cut by half, the error is cut by half. That's the key observation here. So when I'm reporting this method, you know, if I change the value of h, you're going to get different values for the error. I could have started with 0.7 and then 0.35 and half and half. You're going to get different numbers. The numerical value of the error is important, but not the story to tell here. The story to tell here is as I cut h in half, my error is also cut in half. And as h is decreasing linearly, so is the error at the same rate. So it's decreasing at the same rate. This will have very important implications when we solve partial differential equations at the end of the semester. Okay? But I want to use this to do a coding activity. I have like 5 minutes left, 7 minutes. I don't think we can do it. Maybe we do it. Okay, let's just do it with the just hard code it. Okay, and on Tuesday we will do it the fancy way. So again, I want for the function f of x equal 2e to the 0.5x, create a Python routine that computes the relative approximate error. But now I have a bunch of values for h, because now you're using Python. Actually, in one of the homework assignments, I'm going to give you 1,000 values for h. You're going to compute them in one shot. Okay? So, but now we're going to do it for h equal 8, 4, 2, 1, 0.5, etc., and look at the error. Okay? So we'll do this in Python. So you can open up a new Jupyter Notebook if you want. So let me get this guy out of the way. Again, the point is not to teach you too much about error, but just to show you the process of thinking about things, but coding is the goal here. And we're going to code more on Tuesday, next Tuesday. I was hoping to do some more coding today. Okay. All right, so go ahead and start a new Jupyter Notebook. Okay, and I would name the notebooks, so you have to pardon me for not following proper practices because I don't have time to do all of this in class. But you know, round off error demonstration. So that was the first one. So I'm going to create a new notebook next. So I'm going to go again and do new notebook. It doesn't put it here. Apparently, it puts it on the. Okay, so I have a new notebook that I created here. Okay, window, move. Okay, So we are going to, with this notebook, we're evaluating relative approximate error. Okay, relative approximate error demonstration. All right. And you know, I want you to put your name, etc., but I'm not going to do this. Again, I am assuming that you will do this in your assignments and your reports. But here in class, I'm just going to hit the code because I don't have time to type all of that discussion. So our first approach is going to be, we're going to do a brute force approach, which is essentially using Python as a calculator. So I'm going to take each h value and compute the derivative, approximate derivative, and compute the error and print it out. If you do it this way, I'm not going to be offended or take any credit from you. You can do it this way. I'm just telling you it's not the most appropriate use of Python. Okay? But maybe you're just starting and you're just learning things. It's okay to do it that way. But I want you to try to challenge yourself to think of cleaner ways of doing it. So we're going to do the brute force approach, and then we're going to improve that approach with a couple of different methods to show you the difference. Okay? So here I want to do at x equal 0.3. Okay? And what I want to do, starting with, so if you, let me move my slides so we know what we're trying to do. Move to pressed on. Okay, so we're doing this function, 2e to the 0.5x, and we're doing this approximation at these h values. Okay, great. So what I want is an h value. I want a mechanism to compute this exponential. So how do I get the exponential in Python? I'm going to import math. So to add a coding cell, you can just select the cell. Okay, so select the cell. If you type A, the letter A on your keyboard, it adds a cell above. If you type the letter B, it adds a cell below. Okay, so I'm going to press A, it adds a cell above. If I go here and press B, it adds a cell below. Okay, so I need to add a cell above, and I'm going to say import math. Math. Pretty straightforward. Math is a library in Python that contains some cool functions, sine, exponential, etc. I'm going to need that to compute the derivatives, the approximation, f of x plus h minus f of x. Okay? So, okay. So for the first thing, my h is equal to 8, correct? H is equal to 8. And my derivative, I'm going to call it df using 8, using the value of h8, is going to be this formula, f of x plus h minus f of x over h. Okay, so what is my f of x? It's 2 times math dot exponential function, and I'm going to put, I have to put 0.5. So this is f of x plus h. So this would be 0.5 times x plus h. Agreed? So it's going to be 0.5 times x plus h. I already have x defined here, and I have h. So this is going to give me f of x. This whole thing is f of x plus h, right? Because f of x is 2e to the 0.5x. f of x plus h is 2e to the 0.5x plus h minus 2 times math.exp also to the 0.5 times x. f of x plus h minus f of x. Now notice how cool Jupyter is matching your parentheses. So that's the numerator in my formula. And I'm going to divide by h. Okay? So that gives me my derivative at h equal 8. Print df8. Okay, so let's say df with h equal 8. And okay, df8. Unexpected error. So I forgot a parenthesis. Okay, so that's the value of the derivative with h equal 8. Okay? Now, I cannot compute an error here because I need a better approximation. So what I will do, I'll just simply copy-paste this and do it with h equal 4. Tell me, why don't you do it as a function routine call? That's okay. We will do it. We will do it much better. But, you know, we're just getting started for those who have not done Python before. So what I will do is just copy-paste this and do h equal 4. That's the only thing I need to change. I'm going to call this 4, df4. df4. I don't need to change anything except those two things. And now I have another value. Okay, derivative with h equal 8, 15.5. Derivative approximation with h equal 4 is 3.7. Now this is a better approximation than that one, and I can calculate an error. Finally, I can calculate an error. And error, E1, let's call it, it's going to be absolute value of df4, better approximation minus worse approximation, df8 over df4. Okay? And times 100, so that gives me a percentage. Print, first error, say, is equal to E1. Let me fix this. Over df4 minus df4. Okay, df8, absolute value here. Absolute value here. Okay, over absolute value here. Okay, times 100. Okay. So the error is huge. Okay, times 100, 319%. It's a huge error, obviously, because h is a very large number. As we shrink h, that error is going to shrink. So we'll continue with this on Tuesday. And then we are going to do it in a much cleaner way, because this is a terrible way of using Python. If I had asked you to do this for 500 values of h, are you going to copy and paste this 500 times and change, etc.? No. And I won't even use function calls. Function calls are sometimes a thing of the past. We're going to use vectorized array operations to do this all in one shot. Okay, we'll learn that on Tuesday as we get ready for solving systems of equations. Thank you very much, and Godspeed.